Okay, so I'm Arief Budiman. I am currently in Binus University.
Apologize, Prof. Arief. Sorry for interrupting, but we cannot see your screen right now.
Oh, okay. Why is it? Can you see it now?
Yes, we can see it clearly.
Okay, so
Thank you,
sorry.
Prof.
Yeah. All right. Yeah, I'm very happy. I'm very pleased to be here. I think Indonesia is now at the right time, at the right place to take on this battery technology revolution. And I'm really excited actually to be part of it. The work that I've been doing, it's actually the work that I've done in the past few years. But towards the end, I will present a little bit more of the path forward that I started doing here in Indonesia. So this work was done when I was in Singapore University of Technology and Design. So basically up until early last year, I was in SUTD. Only mid last year, I started in Binus in Indonesia. So I'm going back home for good. Okay, so this work is in particular is in collaboration with MIT and Stanford and Berkeley. So yeah, as you can see there, we have collaborator in SUTD, in MIT, and in Advanced Light Source Berkeley Lab. Okay, so what's the agenda today? So if I'm not wrong, correct me if I'm wrong, Prof. Effie. I think this school is also being organized by the Materials Research Society of Indonesia. So I assume that many of you would be material scientists. Yeah, go material scientists. So I'm also a proud material scientist. As I've been introduced just now, my PhD is in my master's. Actually, my 2 master's degree are in material science. I have 2 master's degree, and my PhD degree is in material science as well. Although my bachelor degree is from Teknik Mesin in ITB, but I am by training in research. I'm a material scientist. So I will be talking a little bit more about, I think it is good for me to emphasize a little bit more about advanced material characterization that we use here in our battery study. But very shortly, we will talk a little bit more about anode. I heard the previous speaker have been discussing about anode and cathode and the different variety of the technologies that are available right now. But I will be talking more specifically on anode material and on what at least some of us and many of us think that what would be the future of anode. What we think is the future is silicon nanostructures. That is full silicon. As you know, right now, anode consists of mostly graphite. So it's a graphite-based anode with, according to Tesla's announcement, I think if many of you probably have also followed Tesla very closely, Tesla is currently the technology leader. I think I'm a big fan of Tesla. They also have already a load, or at least, or in other words, dope with silicon. So they have like a silicon dope graphitic based anode. But we are talking about something completely different. We are talking about 100% silicon, and it is silicon nanostructures. So we'll talk about that. But before that, the next one that I'm wondering if the participants can see my cursor. Hello?
Okay, no problem.
Oh, okay. You can see my cursor, right? So I can point.
Yeah, we see.
Thank you very much. Okay, so that's why for this talk, I purposely would like to emphasize on an advanced materials characterization technique that, in fact, I've been specializing since my PhD time. Well, in fact, this synchrotron micro X-ray diffraction is indeed really what my PhD is all about, and what my early work in research is mostly based about. I believe I share this with I share this early training or this training and the early career research field in synchrotron or neutron diffraction based with Prof. Effie. We are both a diffraction person, and in terms of materials characterization technique. Okay, anyway, so we will use this, we will talk a little bit about this advanced materials characterization technique, because I think, simply because I think the participants are, many of them are material scientists, so I think they will benefit from, this is one of a very recent cutting edge tool. It's basically X-ray, but it's just like orders of magnitude better X-ray. Okay, so we will use it to study the characterization, to study what's the performance of nanostructure anode in silicon. Perhaps I will move very rather fast on the experimental, because I think many of you here are trained battery scientists, engineers, technologists. So I think you will probably are very familiar with some of the things that I'll be talking about in the experiment, in terms of battery testing, in terms of cycling and decycling. But I think I would the next thing that I would like to focus is on how we propose to enable low-cost 3D nanostructure silicon, full silicon, 100% silicon anode. So we recently pioneered a methodology of additive manufacturing based on electrospinning that would allow this to happen. And this is what I'm doing right now in Venus in collaboration with ITB, and hope that we will be able to report something soon. But okay, without further ado, let's dig into my lecture. So first, we'll talk about the background a little bit. I think this audience need no introduction of why we need rechargeable lithium-ion battery. Electric vehicle is one of the main reasons. You know Tesla, you know Elon Musk, but it's also for a lot of other things. I mean, like laptop has been what we've seen more and more right now, and energy, renewable energy is actually one other application that are that are probably even more important than just cars, right? I mean, cars are, I mean, this car, it's, Tesla cars are hot and sexy, and everybody wants to have it, right? I mean, like, well, I really want to have it, but can't afford it here. But renewable energy is really truly important for the world, for our even existence, our very existence as humankind in this earth. So And renewable energy like solar PV or like wind just cannot stand alone by itself. It has to be with battery, and it has to be battery with the right performance characteristics. And I believe this battery school is also a prelude to the conference of battery for EV and for renewable energy, I think, right? So I think this is really, really right in line into the conference that many of the participants here will be also participating soon, I think, right? Okay, so but really what I'm excited really about is how each of us can, with the right battery technology, so I'm not even mentioning the solar PV anymore, although even though for this vision to work, we need solar PV, but with the right battery technology, each of us will be able to have a zero carbon footprint. Like this house, for example, this is a model house, but I see, I'm still traveling quite a bit to the United States. I have a lot of collaboration in the United States. I also do some consulting. More and more houses or residential houses in the US, in California especially, are like this. It doesn't use any more electricity from outside. It is independent. It is smart. It is it is affordable, I think, right now, more and more, and getting more and more affordable, and it is self-sufficient. The idea is that you generate the electricity with PV. That one is done. The technology is done. We have enough efficiency, enough power supply. But as I said, it cannot stand alone. Why? Because obviously it generates power in the daytime, but in the daytime, most of us are not at home. So in fact, in the nighttime, we will be at home. So then just PV alone will not do. Because obviously it needs battery, or it needs a utility company. But because we want to do away with utility company, the battery here needs to take the front role, the key role. So we have a battery here, so that the power that is supplied by the PV can be stored in the battery and can then be used to for the electrical for the power supply needed at night, because most of us live in our house mostly at night. I mean, in the daytime we have activities outside the house. So and also we can recharge our car. Thus our car will also be carbon footprint. So in this thing, we no longer need electricity from utility. And we know both in America as well as in Indonesia, utility companies are still mostly generating their power from dirty energy, from fossil-based energy sources. So, and this is one thing that I always would like to emphasize, that it's actually almost useless if you have an electric car. You think you are saving the world, but if you are still recharging at home with PLN utility, with PLN energy sources, it's actually the same. It's actually the same, because the power that you use in your battery, in your electric car, is still dirty energy. So this is what I say, what I presented in my slide here. It's really the vision that I'm really excited about. So it's a PV, it's a battery, but it's also a lot of software here, a lot of data science, a lot of optimization, a lot of algorithm that allow this to happen. Otherwise, it wouldn't just be practical or feasible to do or to have this vision. I'm working on a project on something like this, although in the Silicon Valley speak, I would say it is still in stealth mode. That is, it is still in confidential mode, but it's something like this. Okay, anyway, let's dig in. So as I said, I'm a Go material scientist. So battery is all about materials, and materials. You as material scientists have very bright future, especially now battery is taking the prominent space in a lot of technologies in the world, including I don't know if what Pak Luhut with the Kemenko Marves is working on or working out something with Tesla. But if it happens, it will be very exciting to be a material scientist this time in your life, I think, right? Why I said that, because battery is all about materials. Both the anode, both the cathode first. It's all about materials. So we are moving from 1990s, where we have LCO, then we have we start having NMC, we start having NMA, we also have LPF in between. So they are all the different technologies are signified by the different materials that are used, and the different materials almost determine all the electrical performance of the battery, all the electrical characteristic, all the performance characteristic of the battery. And then at the same time, anode is also materials. Anode is also defined by the materials, by the performance of the materials. Graphites are being used simply because it is a very good binder or absorber of lithium ion, and its layer structure system make it similar to the kind of layer that you see here in the cathode, that is deemed to be, that is assumed to be the most efficient way to store ions or to absorb and to release ions. But we beg to differ. We'll come to it too, because we will be talking about 3D nanostructures soon. But anyway, the current anode is graphite, is carbon basically. But soon we will have more and more silicon. Both it is as a dope, as a doping to the graphitic, the graphite material, or by itself, 100% silicon. And not only that, I mean, the electrolyte itself is getting more and more materials. Well, I think the electrolyte is currently, it's not exactly liquid, it's somewhere between liquid and solid. But still, it's kind of still in the realm of the chemists or the material chemists people, right? But soon with the solid state battery, the electrolyte even will be solid. And then it comes to the very realm of us, materials and material science and engineering, because soon the electrolyte will be solid as well. I'm not working on that. I'm working on anode materials research. But I'm just talking that everything is material here. Materials determine all the progress in the performance characteristic, whatever that the battery need to have right now, it is decided by the materials. And it is upon us, I think, to develop the materials. So this is a little bit about what I'm going to talk about, which is 3D nanostructure of silicon. I'm excited about it. But I think this audience doesn't need introduction why silicon is needed. I think if I said carbon just now is absorb or bind lithium ion well, silicon is even better. So silicon is even having like, I think 10 times better than carbon. It has a specific energy of 4,200 ampere hour per kilogram. So this compared to I think compared to silicon, that is only 140. So it's orders of magnitude much higher. Yeah. So and of course compared to carbon as well. So silicon is no question. I think we will not talk too much about why silicon because I think by now it's become clear that the more silicon you have, the better the performance you have. And this performance not only is I'm talking about the absorbing rate just now, but so it's the kinetics, but it's not only the kinetics. Of course, the kinetics is so much better. Kinetics here translate to the charging rate, right? So that's some of the paper in Nature about silicon-based lithium battery anodes. It's a high rate, but it's also higher capacity. So it's both improving the energy density as well as the charging rate. So that's in terms of performance. Energy range, energy density usually determine the range of the battery. The range means that you know, one fully charged you can go like 500 miles on one fully charged. I mean, like Tesla is currently working on a battery that is 1,000 miles one fully charged. Okay, but having said that, I mean, silicon is great, but well, it has problem. The problem is that silicon is a very brittle material, and with obviously lithium ion coming in, it's being absorbed by silicon. That makes the silicon swell, and it may expand up to a strain of 300%. And obviously, in the current form of thin film, so that's what I'm showing here, which is this is the only current form available in the technology for 100% silicon. Obviously, this is not the right form because you can see it's a crack because of it's absorbing very quickly of the lithium ion, but then because of that it expands quickly, and because of that it cracks, it breaks basically. But we are talking about right now nanostructures. So like what I'm showing here. So we are talking about nanowires in this case, or we are talking about like 1D nanostructure here. So so this is with nanowires, it's completely different. Well, we still have stress evolution, we still have possibility of cracks, but we have knobs to adjust. In the thin film form, there is no knob. Well, we have knob in terms of like the thicker of the film maybe, but if we want 100% silicon, that's it. It's, the thickness of the film is pretty much what we can adjust. And we cannot have so, well, then you might think, okay, we might have just very thin, but if it is very thin silicon, then obviously your capacity is not going to be much either, right? Because it is, the capacity depends, or the energy density depends on how much lithium ions you can hold. So obviously you need to have more knobs so that you can have enough material to hold the charges, but at the same time doesn't develop crack. So that's what I'm talking about today. Okay, so we are able to synthesize this in collaboration with MIT. So I actually spent one whole academic year doing research, doing teaching, doing public services in basically being an academia in MIT. It's great. It's the greatest. I really like Boston. So but I really also enjoy the culture of MIT. So we produce these samples very nicely in MIT, and we study it using synchrotron X-ray diffraction. But before we got into that, I mentioned just now, silicon nanowire is not without problem of cracking. It still has problem of cracking. So we see this, it's a silicon nanowire, which upon some lithiation, it start breaking from the outside, as you can see. So you see that the inner core seems to be maintained, but the high tensile stress must be on the outside. You see this, you see that, it all cracked. The crack must be from the outside. So we're not gonna go much deep into this, but this has been studied, and people believe there is this core shell model that is explaining this. Basically, what happens is that the lithium ion goes right into the nanowire, and it starts developing very high tensile stress in the outer diameter and very high compressive stress in the inner diameter. So in the outer has a very high tensile stress, and because of that, it initiates cracks, and cracks grow, and that's what you see here. But this obviously still can be optimized with the dimension or the geometry of the nanowire or the nanostructure. So we are talking about not necessarily nanowire, which is only just 1D. Bayangkan seperti, imagine if you have like grass on the field, basically, right? So you just have that 1D nanowires. But it can still be 2D. It can also be 3D. It can be different kind of shape. It can be for example, it might not be fully wire, it might be a helicoidal arrangement, for example. So all of this can still be engineered, can still be designed. What we want to do is we want to study how still stress develop, and how still stress can, how this can help or enable design that can make us achieve higher performance or much higher performance in the anode. Okay, so with that background being done, we'll go into the characterization technique. So as I said, this is a let me go into this first. This is basically your normal X-ray, except that the radiation, the X-ray source is coming from a facility as big as 5 football fields. It's huge. It's very big. Only several countries, only several advanced countries have this kind of facilities. I'm sure Prof. Evi worked on one. I used to work on one. My students now still are working on one in Berkeley. But it's basically where the particle physicists are accelerating electron in a circular way, because only when it is circular, you can keep accelerating the particles. But as a byproduct of it, we have X-ray diffraction. We have X-ray radiation. And the X-ray radiation turns out to be very useful for material science, which is very useful in terms of very bright, orders of magnitude, much brighter than higher intensity than normal X-ray, than lab X-ray. And because of that, we can focus it down to very small. So now I believe it is already in nanometer scale. So we have a beam of like, it's like you have an eye that can see resolution of like 50 nanometer at this point, I think, in time. Okay, but the other thing is also that, well, I think many of you are material scientists, you know X-ray diffraction, maybe many of you work on X-ray diffraction. Your X-ray, your lab X-ray is a monochromatic. Well, some maybe with white beam, that means it has a range of wavelength, but most of the X-ray, lab X-ray is monochromatic, that is one wavelength, monochromatic, mono wavelength. But this synchrotron radiation is wide beam. That is a range of wavelength. Okay. Other than that, they are all the same. So what I see here is I have the source of the synchrotron radiation. I focus it down to pretty small, but not very small here. And then this is my sample. And then from the diffraction, I get something like this. And from the diffraction, it's just like mirror. This diffraction is just like mirror. It's you from the mirror, you will learn a lot about the crystal that you are studying. And it is the crystal, it is nano crystal that we are studying here in this anode battery. Okay, the experiment goes something like this. So you have basically your silicon nanowire here, you have the battery setup. So even this battery test setup is actually a pretty ingenious work by my student, but it allows lithiation. So this is actually during lithiation, as the silicon nanowire is lithiated, we look with X-ray, and from the diffraction, we learn about what happens during that lithiation in terms of microstructural evolution, stress evolution, and performance evolution. That is kinetics. Okay, so this is the part that I said I will not spend too much time, because I think you all are battery scientists in addition to material scientists. So you can see here it's a carpet of my silicon nanowire. You see that. In this particular sample, we have a nanowire of 180 nanometer diameter with a pitch of 120 nanometer. We have different kind of diameter and pitch. It's just that this one we show as a representative, and then we go deep into this particular geometry. Okay, so this is the sample, the microstructure evolution of the silicon nanowire during lithiation. So this is real lithiation. This is real electrochemical lithiation, because many studies are simply chemical lithiation, which is not real lithiation. This is real lithiation, like what will happen in a real battery. So the lithium ion is being pushed into the silicon nanowire. What happens is that it will, because of the geometry of the silicon nanowire, you see that it will expand first on the top, and only after that it will start expanding to the bottom. But at the same time, as you can see, it will maintain the core of the nanowire to be still crystalline. And as I mentioned in the model that I've discussed earlier, it remains very compressive. And that's basically what I verify with this experiment. So this is what happens during the in situ, therefore the in situ lithiation. You see that after some lithiation, you start seeing this cone structure, and the cone structure becoming smaller and smaller and smaller as this is going down and down and down and down until everything is lithiated. Okay, so this is actually just like what other people have proposed in their simulation. This is not our simulation, but this is basically what happens during lithiation of silicon nanowire. Start from the top here all the way to the bottom, and how the stress is evolving. So you see this again, what I've said about the lithiation is happening and the cone is getting smaller and smaller and smaller. And from the X-ray, I'm going rather fast here because I think we are interested in learning about what happens in terms of the implication of the performance of the battery, right? And also in terms of the path forward. Okay, so here it's an X-ray diffraction. So you will see the HKL here, all the polychromatic ring. So the crystalline ring of silicon nanowires. So we know that the stress develops such that at first it is so it's an intensile stress, and then it starts to develop more and more compressive stress. So this is good news. Good news is that we talk about crack. Crack doesn't happen in compressive stress state. So crack only happens in tensile stress state. I hope for those who are material scientists, you still remember this is probably engineering materials 101, right? I mean, failure of materials, cracks, happens only in tensile stress state, not in compressive. So this compressive stress state is observed the first time by our technique. And it's only possible with real in situ electrochemical lithiation. So this is a proof that we have knob to adjust, a lot knob to adjust if we have nanostructures. That is nanowires in this case. So this is in terms of the performance. And also in terms of a little bit more analysis on the stress evolution. But we basically verified what people have predicted. The model have been proposed, but nobody has ever seen it. We were the first one to observe this experimentally. Okay, so I'm coming to almost the last 5 minutes of my talk. So I think I hope I'm not late. So we see already the benefit of 1D nanostructures, which is nanowires, as we've seen. So we have shown we have an anode that is made by pure 100% silicon nanowire. We are not measuring the capacity in this case or we are not trying to get maximum capacity in this case, because obviously the capacity is not going to be maximum. And that's the reason why we want to go to 3D nanostructure. Obviously, when we have 1D, all the space, the vertical space in between the wires are basically wasted space. These are space that we may use to hold ion, to hold charges, but we didn't. But anyway, we didn't optimize it for that way. We just want to study first using the simplest geometry of a nanostructure, which is nanowire, which is 1D nanostructure, to see if it actually delivered the performance in terms of reliability and kinetics during battery tests. So this is real battery test, real electrochemical lithiation test. And it does. So that's what we have shown. That's the bottom line of my lecture in the last 32 minutes, right? 32, 33 minutes. Okay, but now, so now that we realize that 1D is already so beneficial, at least in creating the compressive energy stress state. Of course, there is some part that is tensile stress state, but with this model that we have, we can then we can adjust it. We can try to design maybe with the geometry of the nanostructure, maybe 1D, 2D, 3D, so that the stress evolution can be the damage evolution can be minimized, so that we will have no crack in silicon, which is the one big main issue of silicon. So we solve it. If we solve this one, we will be able to see. We will be able to have a silicon, a fully 3D, a fully silicon 100% anode. Okay, so but here we are thinking about extending it to 3D nanostructure simply because, okay, if 1D is already so good, then 2D might be even better. If it is not for stress evolution, but even if it is not stress evolution, it is for capacity. Because the more material you can put inside here, the more silicon to hold the charges, the more capacity, the higher capacity you have. So by the way, this work in 1 nanowire is have been reported in several of our recent papers. In Frontiers, in the JMR, in many other materials research journal papers in the last 2-3 years. Okay, but now we want to talk about nanostructures, because with nanostructures, we will have even higher surface volume ratio. So thus we have much larger surface area for absorption. So we'll have faster charging rate. So we'll have more silicon, then we have more higher capacity. But we also have, with the 3D nanostructure, we have very high surface volume ratio, surface to volume ratio. Then we have even better kinetics, because we have much larger surface to absorb at one time, right? So with that, then the problem is how can we create 3D nanostructure? And this is something that only the last 2-3 years, companies in Silicon Valley coming out of their stealth mode and became public, not public company. Enovix is not yet public company. It is still a startup, but at least it is out already of its stealth mode. Before it has been in its stealth mode. The problem is with existing fabrication methodology, it is still very expensive to create 3D nanostructure. So Enovix is already creating a very good methodology, I believe. I have a lot of friends in Enovix. So they have 3D silicon. So this is their vision. So it's not only me. Silicon is already been widely accepted as the anode of the future. 100% silicon, that is, not silicon dope graphitic anode. It's 100% silicon, and it's 3D. So it's not only me. It's this is a company in Silicon Valley, but still, I think we are still very early in the learning curve. This method that they use is still very expensive. I propose a method that is using electrospinning as an additive manufacturing technology to produce, I call it a 3D fiber structure. So it's not exactly wire, because fiber may mean that it's not very uniform, but it's a fiber, and it's not exactly nano, because we don't need nano. But nano is better for example, for charging rate, but it may not be optimum in terms of integrity, for example, of the battery, both chemical integrity as well as mechanical integrity and electrical integrity, of course. So, so I think it's we don't need 3D nanostructure, maybe, but so that we can achieve with cheap methodology like electrospinning. And it's well, the note is only that it is fiber and it is not nano, so it's probably submicron, hundreds of nanometer fiber 3D structure. Okay, so we recently demonstrated this, that it is possible to create a 3D printed fiber structure in some of our. This is 2020 actually. ACS is one of the pretty high impact factor journal, and then recently also in polymers. Okay, so bottom line is we demonstrated the 3D fiber structure. Or by the way, this is the technology of Enovix. So it is still based on wafer level and based on
Prof. The time is
okay.
2 minutes left.
Okay, good.
Sorry.
I'm about to finish. Yeah,
Okay.
I will finish in 2 minutes time. Yeah, I started, I think, before just now at 5 minutes late, I guess, right? Okay. Yeah, so this is the technology of Enovix. I know it is still using pretty expensive fabrication methodology. Okay, but any case, we use what we have termed as electrospinning-based additive manufacturing. We have a couple of modification of the electrospinning methodology, so it's not exactly the same like what you will buy from the market, for example. So we have some modification. One of them is, for example, we have this plate, this parallel plate that allow us to sort of align the fiber so that we can create 3D structure. I think this is just the how. If you are interested, you can talk to me. We can collaborate. But we proved this. This is basically the parallel plate, and this is basically parallel plate with the fiber. Of course, you almost can't see it because it's very small scale. The fiber is, I think this one is actually less than a micron. It's a few hundreds nanometer. Okay, but basically, what we wanted to show is that we have this 3D silicon structure that is expensive, but we have a low-cost way to do it. So we have demonstrated this. All of these are still with polymer, but polymer here is being used as the model material. If you can electrospin polymer, you can electrospin other material, right? Maybe still a little bit of material science problem, but that's something that we can work on. But you see this one and you see this one, I can create a 3D structure, and we even can create like 3D structure that has more different kind of, like this one, helicoidal geometry. We have done with electrospinning of copper oxide anode because it's easier to do electrospinning. So we have done this, and we have proved that we can use electrospinning to create a copper oxide anode. So next, basically what we will do is silicon. So this one is just Sahay is my postdoc. He has done this with copper oxide. So if we can do it with oxide, then we can do it also with silicon. That is our stealth mode work that is right now ongoing, and I'll be excited to report here again if Prof. F.E. invited me again for another conference, another seminar. I will be very excited. Okay, in conclusion, I have shown you one of a cutting-edge advanced material characterization technique that I specialize in, which is very useful. And which results in this first observation of what many people have predicted. Many people have proposed models, but we are the first one to experimentally observe. And this actually, most importantly, it has implication. It has important implication to industry, because this points to the way of how we can create fully 100% but crack-free silicon anode, which we know will have competitive benefits in terms of performance and reliability. The only one big issue with silicon is just the crack. And now with this silicon nanostructure, we will have high performance, high capacity, high charging rate, while minimizing or reducing away completely, doing away completely with the crack issues in silicon. This is why I think this is a very exciting time for us material scientists. The battery is being defined by the material that it uses. Lastly, I want to propose to have electrospinning-based, modified a little bit with additive manufacturing methodology for low-cost 3D nanostructure, 3D fiber anode. I have to correct this. Okay, with that, then some acknowledgement, and I'll be happy to answer some questions if there is any.